Today I will present you the geometric concept of a novel reconfigurable structure for architectural applications. A review of transformable structures for building application has indicated that transformable frames, such as reciprocal or scissor linkages of flat or curved configuration, if properly designed, are able to carry loads and can serve as space-defining structures. However, a usual challenge in the design of a transformable structure is that its outer boundaries change during deployment, while the rest of the building parts remain fixed. Furthermore, transformable frames usually require the addition of a surface covering system, such as a flexible membrane or origami folding members, as we see in the lower figure. In this case, an additional challenge may be posed by the degrees of freedom of each system or the motion path that the parts of each system are following during deployment. So, the main objective of the presented research was the development of a novel reconfigurable structure that is based on the combination of a transformable frame and a special category of origami folding members that address the above-mentioned challenges. The basic component of the developed structure is a star-like reconfigurable module. This module is a space frame formed of two layers. Each layer consists of 6 identical isosceles triangles connected to each other with revolved joints at the vertices of their longer sides. The two layers, they form a continuous closed network. The so-developed reconfigurable frame can transform from a star-like configuration to an almost circular one. More specifically, the star-like shape is a convex form with 6 endpoints that gradually transforms to a concave one of hexagonal shape, which, when fully deployed, becomes a dodecagon. The geometric analysis of the star-like shape has helped in calculating the radii of the abounding outer circles of the star-like unit during its deployment. As we see in the hexagonal configuration, the radius of the enclosing circle is 2L, where L is the length of the equal sides of the triangles, while in the final configuration, that is the shape of a dodecagon, the R is 1.9L. It is important to note that the radii of the circumscribed circles of the star-like structure present only a small deviation from the initial convex to the final concave configuration. To analyze the kinematic behaviors of the star-like module and to simulate its motion, a geometric reduction of the space frame structure to a simpler one has been conducted by replacing the triangular frames with the triangular surfaces. The schematic diagrams indicate that for the analysis of the motion of the frame structure, the star-like module can be considered as an angulated scissor linkage, where the two equal sides of the triangular surface elements represent the triangulated scissor units that form the scissor network. The angle theta represents the angle between two consecutive angular scissor units, and by changing the angle theta, all intermediate configurations can be generated. Also, the so-defined scissor structure presents a degree of freedom. Now for the study of the surface members that will be used in combination with the star-like scissor unit, we had to take into account that the scissor linkage systems presented 1 degree of freedom. So a search of the existing origami crease patterns has identified several folding patterns that also present 1 degree of freedom. Specifically, an origami crease pattern that forms an orthogonal prism of hexagonal base in its compact configuration, and a surface that expands in a direction that's perpendicular to the axis of the prism in its deployed one, was selected as the most appropriate for this case. The dodecagon that we created by a slight variation of the initial scheme can be attached to the 12 vertices of the star-like unit in its fully deployed configuration, while the hexagonal shape at the end can be attached to the vertices of the hexagon at the fully compact configuration. The values of the crease pattern angles have been calculated and used for the kinematic simulation of the origami surface. In this figure, we see that as the star-like unit deploys, the origami surface expands until it provides full coverage of the star-like unit. And here we see the process of the origami surface integration. The efficiency of the developed reconfigurable star-like module has been tested and evaluated with kinematic simulation standard, but also with small-scale physical models. And here we see the integration of the physical model of the origami surfaces. Larger reconfigurable structures composed of interconnected star-like modules have also been investigated. And we see the shape of the star-like module has determined also the shape of the number of the units that were used for a stable assembly. The modules are connected to each other at the vertices with revolute joints. And as we see here in this figure, we see with red dots the exterior vertices of the central module. And it's important to mention that this structure also presents a degree of freedom and all interconnected modules deploy simultaneously. Here we see the development process from the star-like unit to the multi-unit structure. And the physical, we see here the physical model of a 7-unit structure before and after the addition of the origami surface members. An initial schematic idea of a reconfigurable structure composed of star-like modules that is used as an overhead structure is shown in these figures. And we see here the deployment of the canopy structure. And of particular architectural interest is the changing light-shadow pattern that is projected on the surface below the canopy structure, as we see it. And here we see a perspective view of the interior space and the detail of the canopy structure. Finally, future work in this direction will include studies on variations of the star-like module, as well as adaptation of the concept to current configurations. In this case, the modules will occur from a geodesic subdivision of the spherical geometry, and they will be composed of 2 different modules with 6 and 5 vertices, respectively. Thank you very much.